Hi and welcome to another episode of TRX Bench. Well, you may have seen my last video 153 where we restored an old HF-Kit signal tracer IT12. And you may have seen me testing the capacitor, the electrolytic capacitor, in this unit with my ESR meter. And I had some questions if it is really possible to test a capacitor only with the ESR and then subsequently telling if this capacitor is healthy or if there is a problem with this capacitor. Well, this is what we want to look into a little bit today, because it is very interesting to understand a little bit more about ESR, and that is what I found out in the discussions with some friends here locally. And therefore, let's try to understand how it hangs together and why, for instance, we can test the ESR in circuit. So you may know that a lot of, or mainly all components needs to get resoldered, so taken out of the circuit, and then you can test the component. And why is it possible to test an electrolytic capacitor in circuit, but only the ESR? If we are looking for the capacitance or maybe for a dissipation factor or such, then of course we have to take it out as well. And that is where the question is coming from. Well, is it really enough to test only the ESR? So let's look and see, and let's find out, shall we? Alright, so that is pretty much the same capacitor, electrolytic capacitor, which we had in our HF-Kit IT12 signal tracer. So it is also 50 plus 50 microfarads, so this is a double pack, and it is designed for 350 volt, so it is pretty much the same capacitor, and it is roughly the same age. And we have always the question in service when we check a radio or any electronic device, we need to get an answer if a capacitor or any other component in our circuit is in a good condition, so that it can work in the circuit, that it does not make any trouble, and therefore we need to find ways to evaluate if something is good or bad. And therefore we have really a lot of different ESR meters on the market, and believe me, what we see here on the bench are only the cheap, crappy devices which you can buy. So the real professional ESR meters are much more expensive, and therefore it is most time not affordable for a hobby lab. So we have to take this here, and that is the reason why we use this. But believe me, nothing wrong with this ESR meters, so they really work just fine. Well, maybe let's talk a little bit about ESR meters and the history when ESR meters were not on the market. ESR meters became very important and popular when this, SMPS switching mode power supplies entered the market, because with this switching mode power supplies we recognize that suddenly we have a lot of problems with electronic devices, and we recognize that we did not really get power, so that means voltage out of our power supply. But to be honest, if you talk to older technicians, you hear that right in the beginning, when all these switching mode power supplies came into more and more electronic devices, such as TVs and video recorders and stereo equipment and what have we, you know, nobody really recognized that we have really huge problems with capacitors. So they get this power supplies on their workbench and they recognize something is wrong, and they started their troubleshooting with, what is with our rectifiers, what is with our transistors, and what's with our ICs, and what have we. And you know, they started the troubleshooting as they had the experience with breakdowns like this. And in the past, electrolytic capacitor faults was known as well, but you know, it was a little bit different. So you have seen electrolytic capacitors leaking out, so physically leaking out. I do not mean the internal leakage current, which we discussed in our video 91, where we talked about electrolytic capacitors and leaking current. So that is not meant. What I mean is that the electrolytic capacitor is really leaking out, and you can see it on the board. There you can then have then you can see the acid in on the board, which is really destroying the traces, right? So that is a different story. So that was known. It was known that sometimes a capacitor really shorted out, and of course it was known that the capacitance itself dropped or exceeded. So that all was known, but that a capacitor completely was failing in a way that the complete SMPS will not work any longer. So that was not really known. So, you know, with this upcoming SMPS and the heavy duty under which circumstances the electrolytic capacitors have to work in a SMPS were different. So, you know, all the pulses from switching on and switching off the switching transistor makes it different. So the capacitor get hot, and the electrolytic evaporated, and then you know, the capacitor dried out very, very fast, and suddenly this capacitor don't work in this switching module, and that means that the SMPS stopped working. And in the beginning you very often heard, all right, just change all the capacitors. I mean, that was a good idea, because when all capacitors were swapped out, then you had the guarantee that it works. But nobody really understood in the beginning why it is this way. And well, let's try to understand a little bit what's going on in our capacitors. And that all simply means that we needed a new method to check out our capacitors. I mean, this ESR, which is nothing else than the equivalent series resistor, so that all has been described in our video 83, where we talked about LCRs, meter, DQ, phi and ESR. But now we just want to only look into the ESR. So it was known that there is a series resistor within any electrolytic capacitor, and we are able to test it with an ESR meter like this. And you see it is connected here, and you see we are reading an ESR of 0.273, which is very low, and we all know by now that only a low ESR is very, very important, because if we have a high ESR, then voltage will drop at the ESR, and that means there will be power then internally. The capacitor itself gets hot, and then you know the drying out process started until the electrolytic capacitor is completely dried out and stopped working. And therefore we have here our ESR value, and you know all these tables, and you see, for instance, here's our 47 microfarad value, and you see with 250 volt it should be below 0.8 of an ohm, and that means we are 0.27 of an ohm, and that means this capacitor is reading good and we can consider it as good. And really, this little neat lab helpers really makes troubleshooting so much easier in electronic devices. And well, by simply reading the ESR, or able to read the ESR, we can tell something about the capacitor. So we can say something about how is the aging going on with this capacitor, and that really let us conclude on the condition and the health of our capacitor. Okay, so let's try to build a model that we can understand what's really going on. So I have simply here 1000 microfarad 25 volt capacitor, and when I connect here this capacitor to our ESR meter, then we read 0.087, and it is, as I said, 1000 microfarad and 25 volt, and that means this capacitor should be better than 0.8, and maybe this is already a little bit out of tolerance, but it is an old and it is a crappy one. It's just here for our little experiment, and of course I haven't really calibrated the meter anyways. That all doesn't matter right now. So what I just want to make you clear is how does the equivalent series resistor works. And in general it is nothing else than a normal resistor, and you see here we have here a resistor, and with an ESR meter, let me go out of zoom here a little bit, with an ESR meter we can also test our resistor, right? And you see I'm testing here only our resistor, which is between here our Kelvin clips, and you see it is 3.3 kilo ohm, and the color code is orange red, which is telling us yes, it is a 3.3 kilo ohm resistor. And this little one here, we can use the same procedure, and you see it is 9.9, so this is a 10 ohm resistor. Okay, so that means this really can be used as an ohm meter as well, but it is a little bit different because we of course have a capacitor, and we all know that with a normal ohm meter we can't test the capacitor, as the capacitor is blocking DC. So therefore this must be a little bit different. But let me simply put here our resistors in series, and now we see that what the hell is this? So we really now testing 3.349 kilo ohm, right? And that is a model for what is happening inside a capacitor. I mean, it is not exactly what we have. I mean, there is much more going on inside the capacitor, but to understand what it is simply a resistor in series, and we can reproduce it here simply with a normal resistor in series. Okay, and as we can't test this little model with a normal ohm meter, this is something different, our ESR meter, and we have learned that we have to test our ESR with 100 kilohertz, sorry, with 100 kilohertz test frequency, and only with 100 kilohertz we are able to compare against the manufacturer's datasheet, because they test their capacitors today, I guess all test with 100 kilohertz. So that is, it is not a norm, but yeah, it is more or less, I guess, a gentleman agreement. Everybody is testing with 100 kilohertz, and that means I have here connected here my scope probe, and you see here that is our test signal. It is a nice and clean sign, and let me see if we can read the frequency as well. So you see it is really 100 kilohertz. So that is the test condition, and that is the reason why we finally can test over, really over a capacitance, because otherwise, as I said, with DC it would be blocked, so we cannot test it with a normal ohm meter. All right, and I hope anybody knows this little diagram. So that is a series equivalent circuit model of an electrolytic capacitor, and that is what we have seen in our earlier videos as well. So you may already know that we are living not in an idle world, so our capacitance is really not on its own, so it always has the ESR, and of course as well ESL, and which is the equivalent series in inductance, and of course we have our leakage resistor, which we talked about in video 91, but for today we only interested in our capacitance itself and the ESR. And now you already may wonder if we have our capacitor in our test circuit. I mean, that is what we have seen here. So I have simply put here a resistor in series with our capacitance. Then we always have, of course, here our capacitor in circuit. And how is it then possible to test here for our resistor, right? So this is what we want to test, but this here is, if you like, in the way. So we really need to understand how we are able to only read here our resistor. And again, if we only test here our capacitor, I mean, this one is not really faulty, so it is more or less healthy. So all right, fine, let's accept that for our test here. And we see we only have 94 milliohm, right? If I now put here our resistors in series, so we more or less are able to read only our resistors. And this little resistor does not make any problems. And the question is, why is it so? Why does our capacitor here not really makes our test result in any case odd? So I mean, that is the question. I mean, why do I read this capacitor only on this low ohm value at least? Yeah, and you may have wondered as well why on these tables all the values are so small in the milliohm area. So, you know, that is, you may feel, hey, such a low ohm value, so what's going on? Why is it so? And that simply is because our capacitor is frequency dependent. So that means if we find a frequency which would more or less here eliminate our capacitor out of our test circuit, then we really only would test here for our ESR. And that is what we are doing with our ESR meters. So we use 100 kilohertz, and with 100 kilohertz we more or less are able to reduce here our C to really a minimum. Well, a little mass, but I try to keep it as simple as possible, but I think that might help just a little bit to understand how it really works. So we are able to calculate our capacitor's AC resistor, which is called XC, right? And this here is our formula. So our XC is equal with 1 over 2 PFC, right? And we know we use 100 kilohertz as test frequency. And for instance, we tested here our 1000 microfarad capacitor, and that means 1000 microfarad is equal to 1000 times 10 minus 6. So that is what 1000 microfarad is in a form which we can put in our calculator. And I have simply taken here our formula and I have put it here into my calculator, and you see it is exactly what I have put down here on our piece of paper. You see 2 pi times 100 kilohertz times 1000 microfarad. So that is the formula. And when I now hit here our equal button down here, we should get our AC resistor of this particular capacitor with this particular 100 kilohertz frequency. And I hit it, and what you see is that the maximum resistor with 100 kilohertz and 1000 microfarad is 1.5 milliohm. Aha! So you see, we are testing here for 98 milliohm, okay? 98 milliohm. So that is our test result here with our 1000 microfarad capacitor, okay? But if we would live in an idle world, then we only would see let me call it 1.6 milliohm. Okay, we only would see 1.6 milliohm. So that means that the rest here of our test result is already our ESR. Okay, so if our capacitance is just fine, we should not read a higher ESR like this, and we know that a portion of this test result is the AC resistor of our capacitor, and that is approximately 1.6 milliohm. Okay, and that also means that a healthy capacitor already have a ESR, even if it is very low. But the ESR is simply here our wires which needs to get bonded here to our inner layers and what have we, and simply by doing the bonding we will get a little resistor, and that is what we finally read here on our meter. Well, but additional to what we have already heard up to now, there is another little thing we have to think about, so we really need to have it in mind. So if we would have, let me say, 2 normal resistors like this here in series, okay? So that simply would mean if we would draw the resistor of both resistors as a vector, all right, then we could say, okay, this vector is bigger because this might be 100 kilo ohm, and this only let it be 10 kilo ohm. So we have one vector, okay, and we have a second vector. Okay, that is too much because the length here of our vector is telling us how big the resistor is, and we know that this vector should be equal with 100 kilo ohm, and this vector here should be equal with 10 kilo ohm. And we could calculate it here on a graphical way, and graphically that would mean we can add these both vectors together because they simply add up, and the new vector, which is the sum of both resistors in series, is 110 kilo ohm. And so we are able to calculate something like this in a graphical way. So we use simply our vectors for things like this. But we are not talking about two resistors, so-called real resistors. So we have a capacitor in our circuit, and the capacitor is not acting like a normal or real resistor. So this capacitor will produce a phase difference in our circuit. And that is what this graph here is telling us. So we see red is our voltage, okay? So this is our voltage, and you see that voltage and current at our capacitor is not in phase. So you see a phase difference of 90 degrees, and that is always if you put a real, so-called real resistor and a capacitor or a coil, so an inductance, into a circuit, into a combination, then you always get a phase difference, and that is what we are facing here as well. Okay, now slowly, really slowly, step by step. If we have a capacitor, right, and we connect our capacitor to a DC, what we see is a charging, all right, and a discharging. So this is the charging behavior of a capacitor. At our start point, so when a capacitor is completely uncharged, so fresh, not in circuit, not switched on, however you want to call it, you see that if we put energy into our capacitor so that we maybe switch on the voltage, then you see that our voltage is rising very, very, very slowly, because in the first moment when you switch on a capacitor without any resistor in front or such, then the only current limiting element is our ESR, and you see with a very tiny resistor we only have a very, very low voltage drop, and then the capacitor starts charging. So that means that the resistor is getting up more and more and more, and when the resistor is coming up, then the voltage drop is getting greater, and finally our capacitor is fully charged. And when we now disconnect our voltage but our capacitor is still at a load, then the capacitor starts discharging in the same manner, and that is what we can see here. And we can prove this behavior also here with our little insulation tester. So I have here connected a capacitor, and what we do is we put DC to our capacitor, and as this is a 2.2 microfarad type, it takes a little while until it is fully charged. And let me press here my button, and what you see is exactly what I told you. The needle is getting up, and you simply see that it starts from a little resistor up to a high resistor, and you know this should be a DC blocking component, so we want to see it fully blocking really our DC, and that means we need a very high resistor. So let me simply press here my button, and you see that my needle here is slowly working up its way to really a high resistor. And yeah, I mean the inner resistor here of my insulation tester is quite high, so it really takes a while until a 2.2 microfarad capacitor is fully charged. But you see the tendency, and that is what I wanted to show you. Again, that is the behavior what we have seen here on our little insulation tester, right? So the voltage is getting up, is climbing up, because the inner resistor is changing. So the capacitor is charging, and while it is charging, we get a higher resistance, and that is what we can measure here on our little insulation tester. Okay, and now with the knowing of what we have learned before, you may already understand what we see here. So you see that the voltage is coming up by time, okay, and in the same manner our current is dropping down, because when the capacitor is fully charged, then it is like a DC blocker, a very high resistor, and therefore no current is flowing here any longer, and then we have the full voltage at our capacitor, right? Well, you already may wonder why I tell you all this. I mean, we are playing here with vectors, so we are playing here with two resistors in series, and we said that both resistors have a behavior that we simply put the both vectors one after the other, and then we can add it up. And we have heard that we have a phase difference between voltage and current, so that is what we have seen as well, and that is because we have a capacitor in our circuit, and a capacitor always makes a phase difference between voltage and current, and because we are dealing here with a capacitor and a resistor, we have to take our phase difference in consideration. Again, why? Because we have found that our AC resistor of the capacitor is with 100 kilohertz very, very low, but we can't add it like we have done it here with our resistors. So we have to take our phase difference into consideration, and therefore I tried to explain a little bit about the charging behavior of our capacitor, because then you might be able to follow the next step a little bit easier. Because now we are dealing with this model here. So we have our sine, and we have seen that the output of our ESR meter is a nice sine of 100 kilohertz. So let this be the sine which is coming out of our ESR meter, but it can be any other sine, whatever you like. And what we try to explain with this model here is that we are saying here at the start of our sine, just at that point here, we have 0 degree. In the middle here, okay, it is 90 degree, and here we are at 180 degree, and then we go ahead until we are here at 360 degree, or it is as well 0, because we are again at the starting point. And that means at any step here on our sine, we are at a specific phase angle, and that is what this model describes. And of course this here can be minus 90 degree, or of course depending on which model you are working, 270 degree, of course. And to make it as a good illustration for us, we assume that this vector here, because that is the reason why I put this little vector, is rotating always this way, right? So at this point, this vector, we can go over here and we can exactly describe this little dot here on our sine. So far, so good. Now let's go back to our series configuration of resistor and capacitor. And what we know is it is a series configuration, and in a series configuration it is always at any point of our circuit we have the same current. Okay, so the vector of our current, let's draw it in red. So this is always at any point of our circuit, it is always the same in a series configuration. And in phase with our current is always the voltage drop at our resistor, at our real resistor. Okay, so let this here be our real resistor, R. This is R, and this is of course XC. Once again, if we would put an amp meter, it doesn't matter if we put it here, if we put it here, or if we put it here, we always would read the same current through our model here. Okay? But in a series configuration, the voltage drop is always different. So we can, for instance, go back here to our both resistors, and of course we have a voltage drop at our 100K resistor, and we have a voltage drop at our 10K resistor. And the voltage drop at our 100K resistor is of course higher than the voltage drop at our 10K ohm resistor. So more, less voltage drop. So that means that in a series configuration we have always different voltage drops at our different components. Okay, the only exception is if both would be, let me say, 100K, and if we have 10 volt of complete voltage, then if both would be 100K, then we would have 5 volt at each resistor. So of course that is the exception, but in any other configuration, so if there is a difference between the values, then of course our voltage drop is different and it is not always the same like it is with our current. Okay, back here to our model. So we know if we put a voltage to a resistor, okay, then we have directly the voltage at our resistor, independent if we test it here or we test it here. We directly have our voltage drop at our resistor. It is a little bit different if we have a capacitor in our circuit, because, and that is why we watched our charging behavior. So we have seen that the voltage is coming up very, very slowly, dependent of course of the value of our capacitor and some other components which might be somehow dealing with this circuit. But anyhow, we know that the voltage is coming up very, very slow, and that means that the voltage is finally later to be measured at our component. So if we pick here the voltage at our capacitor, so we see the voltage later as we would see it as at our resistor, and thus we have to draw our resistor like our voltage later, because voltage and resistors are always proportional, and therefore if you have a big resistor you have a high voltage, and if you have a low resistor you have a low voltage drop. So both behavior is always equal or proportional, and thus we have to say our resistor at our capacitor is later. So we see it coming up at 90 degrees later. Go back here to our model. So we said that this here are the vectors, and if this is here 0 degree, okay, so if there is another vector at this point where I have put it in here, if that would be a second, let me call it simply sine, so a second sine, then it would be a little bit earlier. So that means a second sine would start here at that point would rise, and that would look like, I'm not the best drawer, but I hope you get the idea. So you see, this is coming up earlier and this is later. But if we are down here, so that is definitely later, right? So exactly 90° later. And if we would put that here into our circuit, that would look like this graph here, the black one, okay? So you see it starts at 90°, which is of course later, okay? So that is the important conclusion. So we can say in which way the different phases are coming up, and that is what we try to describe here with our little vector diagram. And now you see it is not in phase. So what we have here is our XC, right? And you see the voltage is later than the voltage at our resistor, and therefore this is telling us how it works together. And basically it is exactly the same as we did it here, okay? So we put the both vectors one behind the other, and then we added it up, and we do here basically exactly the same. So at the end of our first vector, we put this vector here in the same resistance, and that means we only put it in parallel from here to there. So at the end of this vector we put the starting point of this vector. So now we have both vectors behind each other, and now we are able to find out our resulting resistor. And the resulting resistor, and again it is the same like here, we added it up, and we do here exactly the same, okay? It's exactly the same means. So we can now add in a graphic way both vectors, which is this here, and that means this here is the resulting resistor of our little example here. So why I'm telling this is very simple. So we have seen that the XC is due to the fact that we are working here with 100 kilohertz, very tiny. And if we try to draw it once again in the real way, then we see that here is our ESR, okay? And we have calculated with 100 kilohertz, we calculated this with 1.5 milliohm. So that means our XC is really this tiny that we cannot really see it. It is really so tiny. And if we take now this little arrow and put it here at this side, and we do our graphic calculation, and we put here the resulting vector to it, then you see that our resulting vector is more or less really the ESR, because the little XC here, our little XC is here so incredibly tiny that it does not have any impact, and that is the reason why we only measure our series resistor. Okay, and even if our capacitor is aging and our ESR is getting up maybe in this dramatic way, okay, so the blue is as it is normal, and now it is really huge. But due to the fact that our XC is still very tiny, the resulting graph is again only our ESR, and that is really the beauty. We always can really tell how large or how huge our ESR is, and we can really conclude by knowing our ESR, we can conclude on the quality of an electrolytic capacitor and how far is already the aging of our capacitor. And I mean, if we find a capacitor which is out of tolerance, so that means if we see that electrolytic capacitor is higher than what we have here on the table, then that is a clear sign that aging has simply started, right? So we know something is happening inside the capacitor, which is clearly telling us, hey, this capacitor is aging, and it is only a question of time until this capacitor is failing. That finally means no discussion. If we find a value which is higher than what we see here on our table, we simply change our capacitor. Wow, that was a lot of stuff, and even you have never heard about that before. So a lot of theory, a lot of blah blah. So let's have a break here, and let's do a second part, and in the second part we do only experiments, so no more theory, but I hope you get a basic understanding how this all works, and now we can go a little bit more into practical experiments to see if the capacitor which we test with a low ESR is really healthy. So that will be our next step in part 2. Now for part 1, let's stop here and let's make a break, and we go ahead very soon.